Okay, good morning, everybody. Good morning, good morning. My name's Terry Adamson. I'm the Technical Director with Fenestration Canada. I'd like to welcome you to our third annual Canadian Glazing Conference at the beautiful Park Hotel in Vancouver. I imagine we're probably missing a few people that are fighting traffic to get into Vancouver, which is always a problem. So our third conference, we moved it to this hotel in downtown to try and get some more space. We'd outgrown the other one in Surrey, so here we are. Donated at the casino last night, so nobody else needs to go. So I've covered everybody's casino cost for the day, so don't worry about that. We've got four really great speakers for you today. My mic keeps dropping out on me. Hello, hello, hello. Can you? Maybe it's just me, because I'm not hearing very well. Leonard Pianalto from RJC is going to be with us this morning. Cam Drew, Fenestration Canada, Shiva Zargar from Build Neutral, and Jonathan Hovey from Sherwin-Williams we're going to hear from today. So some great speakers, hopefully bring you some good content and teach you a thing or two. It's been a really busy time at FenCan this spring already. Lots going on. We were at Fensterbouw week before last. Fantastic show. Had a really great time. Met lots of really great people. Always recommend going to Fensterbouw. You'll learn things about the fenestration industry that you didn't think were possible. So if you get an opportunity to go in a couple of years, by all means, take advantage of that. Adrian was at Fenestra in Montreal. Where's Adrian? Last week, presented to that group a couple of times, so very active with them as well. And yesterday we had our in-person Pacific Chapter Education Day right here in this hotel. It was really good. We had a good turnout and had some really great content, some good speakers there as well. So really active. We've got FenCon coming up in a couple of weeks in Winnipeg, and then our AGM in Quebec City at the end of May. So lots going on, lots of other activities as well, online content that we're delivering as well. So lots happening at our side. I did quickly want to just kind of point out our team. So we've got Stefan LaBelle. He's our executive director. Stefan, put your hand up just so they know who you are. Thanks. Lane, is Lane in the room? Lane's the one that actually runs everything. So if you get an opportunity to have a chat with her, she'd love to talk to you about opportunities within FenCan. Jeff, is Jeff in the room? No, Jeff's one of our member service and commercial consultants. Lee's out at the Reg desk. He's our membership advisor. So if you have any questions about membership or how you can expand on your membership, talk to Lee. Adrian Edge, he's our codes regulatory director right there. Rich Pareco, he's a consultant that works with us on the commercial side. We're going to hear from him in just a minute. Cam Drew, also a consultant that works for us on the member side and does some podcasts on the business of it all activity within the association. So check that out. And then Mario's our IT, keeps my voice out there so it can be heard. Always doing a great job. Appreciate that. Okay, so as always, we really appreciate our sponsors. Without our sponsors, we couldn't do what we do. We have a fantastic group of sponsors across all of our activities and all of our events and the association in general. They really are able to drive a lot of the content that we provide. So I did want to recognize all of them. Richelieu, which is our top sponsor, our main sponsor for this event. JSA Machinery, Pref ERP, ScreenCo, Opera, Roto, Eugenie, Leighton, Servitech, AdFast, Inline, Paradigm, FSDC. I think that's the first time that they've sponsored us. Is that correct? Is folding sliding door guys here somewhere? Back there? Happy to have you here, guys. Really appreciate it. Bilco, Botero, and Glass Canada. So during the day, we're going to have a couple of breaks, and we really encourage you to spend some time visiting our exhibitors. We've got some out in the foyer as well. So please take a few minutes and go around and spend some time with our exhibitors and as well as our sponsors. So, okay, so we're going to get going right away. First thing we're going to do today is hear from Rich Pareco. He's going to bring an update on the activity around the commercial chapter and the glazing recruitment group. So Rich, come on up.
Good morning, everyone. So I wanted to take a few minutes to share an update with the momentum that we're seeing with the commercial chapter. Because honestly, it's been a strong year. Between our advocacy work on counter tariffs with the federal government, ongoing education with what's going on both here in Canada and across the US, and our efforts to connect the supply chain, we are seeing real engagement. We're also putting a lot of focus on the future of the industry, getting in front of the next generation, promoting careers in glazing, and making sure this industry remains strong long term. The results of it all are simple. People are noticing. They're showing up, and more importantly, they want to get involved. From a growth perspective, our commercial membership has increased to just under 80 members, up from 65 last year. Our monthly meetings are consistently drawing 25 to 30 participants, which is a strong signal of engagement and relevance. At the leadership level, we also have Jeff Shillard from Guardian Glass representing the commercial side on the board, which continues to strengthen the alignment across our organization. Now, one important update. After 2 years as chapter chair, Brent Friesen has stepped away to focus on his business. Brent did an excellent job helping build the foundation of this group, and we thank him for that. This does mean that we're now actively looking for a new commercial chapter chair, and I want to emphasize this is a meaningful role. This is an opportunity for someone in this room or someone that you know to help shape the direction of commercial glazing in Canada. We're looking for a strong industry leader, someone connected, someone who cares about the industry, from advocacy to workforce development to overall growth. It's not an overwhelming time commitment, but it is high impact. So if there's interest or if someone comes to mind, we'd absolutely welcome that conversation. The other area I want to highlight is our glass and glazing recruitment task group. What started as a small initiative has now grown to a working group of both industry members and FenCan staff, and it's evolving quickly. We've realized that this isn't just a recruitment anymore, it's about positioning the industry as a career destination. That includes awareness, training pathways, retention, and making sure people not only enter in the industry, but stay and grow within it. One of the highlights this year was our first ever online career fair in September. We had about 8 organizations from across Canada and around 35 to 40 attendees. It may sound modest, but it's a strong first step, and more importantly, it validated that there is interest and opportunity here. Looking ahead, the focus is on building real infrastructure, better career pathways, stronger partnerships with schools and trade organizations, and practical tools that our members can actually use to attract and retain talent. Because the reality is, the industry doesn't have a demand problem, it has a visibility problem. We all know that. And that's what we're starting to solve. Finally, from an industry presence standpoint, FenCan continues to show up across all key events like the Canadian Glazing Conference, IBS, FenCon, Windor, Fensterbau, and others. All this adds up to one thing. Fenestration Canada is the go-to resource for the Canadian glazing industry. With over 450 members and growing, strong engagement on the chapter level, and real progress on workforce and advocacy, we're in a very good position, and we're just getting started. Thank you. I hope you have a great day today at the CGC.
So yeah, like Rich said, we're looking for a chair for the commercial chapter, and you know, it's not a huge commitment, maybe an hour a month or so, a little bit more. So if you're interested, please email myself or Lee or Rich, and we'll get you connected. So our next speaker is a fellow that I've known for many, many, many years. And it's one of those people that's really well known in the industry. He's out there, he's doing his thing. But I have to admit, I'd kind of forgotten that we knew each other. But I really enjoyed working with him back in the day when him and I were both working with Fenestration BC back in the early 2000s. So for some reason, his name popped up in my feed. I can't remember exactly what it was. Maybe it was a LinkedIn thing or something like that. And I thought, man, oh man, I haven't talked to Leonard in ages. Let's find out what he's up to and if he's interested in coming and having a chat with us. Well, long story short, I'd like to welcome Leonard Pianalto from RJC. He's going to talk about IGU durability. And I'm truly pleased to have you with us today, Leonard. It's been a long, long time since you and I have done anything together. So,
okay, good morning, everyone, and thanks for the great introduction. So I'm just gonna get on with it. Let's see how this works. Okay, I'm gonna start with a story. You wake up in the morning, it's a nice crisp spring morning, kind of like today, and you do what I do and you go straight to the coffee machine, make yourself a coffee. And on your way to the coffee, you look out your window to look at the beautiful garden that you've been tending. And then you see this fog unit. And you think, it wasn't that long ago that I installed that thing. Why is it fogged already? I'm a pretty curious guy and I like to keep good records. So I'm going to go back to look at the project documentation on when I had those windows put in. And here's what I found, a little excerpt from the Division 8 specifications. What do those things say? Well, usually they say the insulated glass unit should have a 10-year written warranty. And I won't read that all out, but it's against hermetic seal failure or fogging. And some more stuff in there. Okay, so there should be a written warranty, right? What's the written warranty say? So dig up the warranty document and you'll see something like this. The warranty period, details, blah, 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 10 years, free from material obscuration of vision resulting from moisture or film formation, right? That's fogging. Okay, so we should be getting at least 10 years out of it. I don't remember it being that long ago that those windows were installed, so I'm thinking, okay, I'm going to call my warranty provider and get those things replaced. But again, my curiosity drives me to want to look at what the industry standards and what the codes say. And the whole presentation isn't going to be slides with words, but I thought this was a good way to get started. So there's the IGCC, which is the, they changed their name, so I always get it mixed up with IGMA, but it's the Insulating Glass Certification Council. So if your windows are certified to IGCC, it means you've tested them either to this ASTM standard or the CGSB, the Canadian equivalent standard. And if you've done that, that means you've met code, because whether it's the Canadian code or the BC code or the Vancouver Building Bylaw, it means that you've tested to either one of those standards. So if you have IGCC certification, it means you meet the code. But if you don't have that certification, it doesn't necessarily mean you don't meet the code. But these standards drive how you test and challenge your sealed units and try and create some standards among manufacturers to challenge the durability of the edge seal primarily to prevent fogging and to maintain the energy efficiency of those windows. Okay, so this gets me into what I want to talk about today, which is, the service life of a window. The expectations around how long your window should last or the time it takes to get it to fog in service relies on the edge seal and primarily its ability to keep moisture vapor out of that cavity between the two sheets of glass. So this is largely driven by the diffusion of vapor through the components of that edge seal. And when you get enough vapor in that space, under the right conditions, you'll get condensation, which is what fogging is. So the seal integrity is directly related to the service life of the unit. And that's really what I want to spend the rest of the talk exploring with you. And this is going to be sort of my collected works and thoughts over 20 plus years in the industry. This is kind of a new presentation, a new material. And it's all my thinking that I've sort of pulled together over this time frame around trying to answer that age-old question, how long should my windows last before they start fogging? So a good starting point, I thought, was to try and understand a little bit or describe a little bit the science behind condensation. And that leads to this psychrometric chart. Now, this isn't going to be a master's class on vapor diffusion physics. I just think that this is an important part of it, is understanding a little bit how condensation works and how it can be reflected and predicted in this very well-defined methodology with this thing called the psychrometric chart. So on the bottom, it's like the air temperature. Those blue curving lines is like the relative humidity in the air, and where your air temperature and your humidity meet, tells you what the dew point or when the condensation forms. So you now are past spring and you're into the summer. You're going to have some friends over for some cold drinks. You start out with some water with ice in it. That gets the water to around 0 degrees Celsius. You check the weather. I don't know why you do this. Maybe you want to know what the relative humidity is when your guests come over. In Vancouver, it can be like 50% relative humidity. That's not abnormal. So you can pretty much guarantee that when you put that glass of water down for your guests, there's going to be condensation forming on it if the temperature is above 10 degrees. So if you think about when condensation forms on the surface of a glass of cold water, that kind of makes sense, right? And the psychrometric chart proves it. So what happens if you put a warmer glass of water out? So I've shown this steaming hot glass of tea. And you know that when you do that, you rarely or never see condensation forming on the outside of it. So why is that? Well, the psychrometric chart says that at 50% relative humidity, and I just picked 27 degrees because that's really a convenient number on the chart here. 27 degrees isn't very warm, right? That would be like your guests would be disappointed if you gave them a cup of tea that was 27 degrees. It's like tepid water. It's like a cold bath. Body temperature is like 36 degrees Celsius. So what this says is that if you put that tepid glass of water on the table, you would only see condensation forming at around 40 degrees. So you're not going to see that in Vancouver. Kind of feels right. Now, say you were somewhere in Asia, Indonesia, maybe where the humidity might be higher, like 90+% humidity, you would only see condensation forming at like 30 degrees, according to this chart. So without explaining too much more about this, what the point is that there's reliable information that comes out of this chart. It's very predictable and it's relatable to like basic quantities that we can kind of understand, right? Relative humidity, temperature, and the surface temperature that we expect to see or not see condensation forming at. Okay, so how does that work within a sealed unit? Well, we got to talk about permeance, which is the rate of transmission of vapor into that airspace. And that is going to be largely driven by the components of that edge seal. So you've got two pieces of glass, and the glass is pretty much impermeable to moisture vapor. And you sandwich that together with the spacer bar. And the spacer bar can be a lot of different things, but just for argument's sake, let's say it's a metal tube, and you can go back and look at the Vitrum table. They have a nice little cutaway. You can actually see what, I'm sure most of you have seen this, but right, a metal tube that's filled with this stuff, and then it's glued to the sides of the glass with a material that, PIB or polyisobutylene. It's basically a glue that sticks the spacer bar to the glass. You try and get that as thin as possible. It's like less than 1 millimeter thick and maybe 4 or 5 millimeters deep, depending on the size of your spacer bar. That generally dictates the amount of moisture vapor that transmits through that edge seal, because it has a very low permeability and it has a very small area. And that is there just to glue the spacer bar in place. And then there's the silicone, the secondary seal, which is sort of the structural glue that holds that sandwich together. When you think about vapor transmitting through that assembly, again, the PIB is sort of the limiting factor because it has the highest permeance or the lowest permeance. Did I get that backwards? Anyway, it is the most difficult for vapor to go through it. And I just use this example of a multimedia water filter when you have a layer of really tightly packed stuff that the water has the most difficulty flowing through. That's kind of like the PIB, and that's going to be the limiting factor of what transmits the moisture into that sealed unit. Okay, we're getting a little more serious about the science here, but again, this isn't supposed to be about moisture diffusion physics, but this is a very important idea here. So moisture or water vapor behaves differently from water, and it follows the laws of vapor diffusion, which is governed by Fick's law. So I'm an engineer, I like equations, so I put one equation on my presentation. Water vapor is sort of the liquid water in its gas form, and it's formed naturally through evaporation. When you heat the liquid up, the particles of water kind of break free and they turn into this gaseous form. And the limit of how much vapor is in the air above the water is dictated by the vapor pressure that's in that system. I don't think I'm explaining it very well, but again, this isn't supposed to be about the detailed physics of the way this works, but there's an equation, and the amount of diffusion that occurs is based on the vapor pressure difference. Usually, well, not usually, but physics says that you go from a higher humidity to a lower humidity. And if you think about that spacer bar, that's that solid red thing where moisture is from the outside environment trying to drive into that dry airspace inside the unit. So in Vancouver, we generally accept that the vapor pressure difference is like 1.5 kPa. So that might not mean anything to anybody, but that's a number that we use to sort of average out over the year to account for the fact that you have very little humidity inside the unit and a variation of humidity outside the unit. And that creates this pressure differential that wants to drive the moisture into the unit through that PIB that's holding the spacer bar in place. Okay, so how reliable is the science? And this is really sort of the basis of my talk. Oh, wait, there's another slide here that's out of order. Okay, so when is the primary seal not good enough? This is like the age-old question, because we know the primary seal is very important to stopping moisture from entering the cavity. And there's not really a lot of information out there. There's this standard that's published by IGMA. It's the TB 1250. And it talks about these 3 standard kind of deviations from what you should expect when you're manufacturing sealed units. So there's this squeeze out. And I think, we can kind of imagine what that means. You lay down this line of PIB as the glue and you squeeze you push the units together, and some of that PIB is maybe going to squeeze out. And so this standard is saying, if you're a manufacturer, you should limit that to about 1/8 of an inch. There's this thing called migration. We've probably all seen that. These little fingers of the PIB that kind of leak out and create this weird looking appearance on your spacer bar. It says that if you have more than 1/2 inch migration, that says that there's something going on with your PIB. So that's not good. It's not really acceptable from a manufacturing tolerance standpoint. It says bubbles can form in your primary seal and your PIB. It says that you should be careful to limit how much bubbles form, but it doesn't give you any guidance. I mean, I don't know, maybe some of the IGU manufacturers can shed some light on this, but there's nothing that says your bubbles should be this big or this small. It just says you should be careful about bubble formation. In the end, this is a qualitative guide for manufacturers and doesn't give any guidance on the effect of the permeance in the PIB or any direct correlation to IGU lifespan. So that brings me back to the science, that Fick's law equation. How reliable is it? Well, I think I've seen that the science, being what it is, can be applied inappropriately sometimes by engineers that are trying to do their best to figure things out. You can't look in a book for the properties of PIB and the permeance values. There's many things that aren't very well defined. So as an engineer, there are certain things like concrete and steel, which are very well defined. You can look in a book and it'll tell you the strength of the steel, and it'll tell you many things about those materials, and you can rely upon them to do calculations to determine an end result. You can't really do that with Fick's law because there's many things that are not defined in that same way. So there's no science that has taken the science and made it relatable to actual reality. That's the whole point of my talk, really. And the results can be very sensitive. You change that little thin strip of PIB, you change that dimension by 10%, and that can have a huge effect on your predicted lifespan of the unit when you apply this law, Fick's law. So here's a story of something that occurred on a project site that I was involved with, where we had some units delivered to site, and they were clearly defective. The edge seal had bubbles in it, and there were huge gaps, and we just said, you can't install those. Those are defective. They don't meet the spec. Send them back. So they didn't like that. They went and hired another engineer who went to site and did measurements. They measured the gap in the PIB, and they said, there's a gap. But they said, that's okay because of all these other things, and we use this equation to determine that there's still 100 years left in that unit. I'm like, okay, well, that sounds pretty good. You're saying that the warranty is only good for 10 years, but now you're telling me it's good for 100 years, even with these gaps. So, we went back and forth in it. And of course, they weren't willing to extend the warranty to 100 years. So that all went away and they replaced the units. But again, this is my thesis here that there is a science behind it, but the science is not well defined in a way that it can be used reliably to estimate a service life, which I know my title is Lifting the Fog on IGU durability, but I'll get there. Okay, so what can you do? There's some testing you can do. There's a frost point test, and I'm assuming many of you know about this. There's an ASTM standard for it. You take dry ice, you pack it into this thing, you stick it up against the window, and you lower the surface temperature of the glass at intervals. And if you get down to like -70 and you don't have dew forming on the inside of that airspace, on the inside face of the glass in that airspace, that's basically telling you that your dew point is -70 or less, which means there's very little or no air inside that cavity, which is what you want. The problem with this test is it takes a long time, and a building can have like 2,000 windows in it. So if you wanted to test all the windows, you'd be there for a long time. Nobody really wants to pay for that. There's this other test, and I want to credit these folks that published this article in the 2024 Ontario Building Envelope Council publication. Hildebrand, DeRose, and Lukes, they wrote this article that suggested that you can use this compressed air test. And it's basically that, that air that you use to clean your keyboard out, compressed air. You turn that canister upside down, you spray it out a window like you see here. And that'll get the surface temperature down to about 45 degrees, -45 degrees Celsius, very cold, right? So you use a digital thermometer to check that. And once you know the surface temperature is down to -45, you just look to see visually. You got to scrape that frost away and look to see if there's condensation that forms on the inside of the unit. And that test takes about a minute versus like 20 to 30 minutes of the other frost point test. So what does that tell you? It tells you that there's very little moisture in that airspace. But if you want to try and use that number to predict how much time is left in your unit, it's kind of difficult to do. So back to the psychrometric chart, you're kind of far off to the left. And again, the only conclusion I think that I can draw, well, you can get sort of deeper into the numbers, but at this point, you can just say at -45 or -70, you don't have a lot of moisture in your airspace, which is what you want because you don't want condensation forming to obstruct your view. Another important part of this whole assembly, which I haven't talked about yet, is the desiccant. So desiccant usually fills inside that little spacer bar tube. And again, there's a nice cutaway back there at the Vitrum desk. There's these little tiny balls, they're like less than a millimeter in diameter. And they're called molecular sieves. So I don't know, that sounds kind of cool, right? But basically all it is a special molecule that has these little pockets that fit a water molecule, and it kind of snaps into it. It just grabs these water molecules, right? So that's how the desiccant works to remove moisture vapor from the air. It selectively adsorbs or traps moisture vapor or water molecules. So the desiccant acts in conjunction with the PIB, the primary seal, to keep the air inside the unit dry, and it works. The PIB stops the transmission of moisture vapor into the unit, and whatever moisture vapor might be in there from original manufacturer or sneaks past the PIB, the desiccant should grab it while in service. So the desiccant is very important, and I'll try and show how important it is to the lifespan of a unit. So again, I'm a very curious person, and knowing that desiccant is very important in the performance of a unit, and you can't really see it, right, other than what you see in books and reports. So I grabbed an old seal unit, and I cut it apart, and took the spacer bar and snapped it in half, and took the what I thought was desiccant, that had to be what it was, in the middle of that spacer bar. And it had that same appearance, these little brown balls. And then I grabbed a little scale, a thermometer and a hygrometer. And then I built this little chamber out of an old takeout food container that I could, modulate the humidity inside. So then I measured the desiccant, just the weight of it, put it on the scale. And over time, you can see there's different dates. And I measured the humidity in the office. It was like around, less than 40% humidity. And then I stuck it inside that little old food container with water in it. And I measured the humidity in there. It was like 90%, really high humidity environment. And what I discovered is that the weight of that desiccant increased with increased humidity. And when exposed to that humidity over time, the weight of that desiccant increased. So I could only assume that it was acting as molecular sieves do, and it was adsorbing the moisture. Now, of course, that's sort of not really reliable to use for anything in terms of calculating lifespans. So I sent the desiccant off to a third-party lab, a proper scientific lab, where they're able to take the sample. You can heat the stuff up really hot, and it ejects all the water molecules out of it, and you can weigh it when it's perfectly dry, and then you expose it and have it come to equilibrium with different humidity environments, and then you measure it, and then you can calculate the amount of water or moisture vapor that's stored in that desiccant. So it's measured as moisture content on the vertical axis in grams of moisture per 100 grams of desiccant relative to the relative humidity. So let's do a little thought experiment. You've got a window that's, say, 1.5 meters by 3 meters or 5 by 10. That's like a standard sort of office size sealed unit. You've got a spacer bar that's like 11 millimeters by 4 millimeters. So you've got a PIB glue strip that's like 4 millimeters on either side of the spacer bar. And then the PIB might be less than a millimeter. You calculate the volume inside that spacer bar. And again, the data isn't really out there, so you have to sort of look where you can to find it. And the bulk density of desiccant that I used arrived at 200 grams of desiccant in this like 5 by 10 window. Just keep that in mind. And then just remember this. Well, I don't know how easy it is to remember this graph, but there's this curved line that's moisture content over relative humidity, right? So then you take that and you mash it together with the psychrometric chart. And you just have to trust that I did it right, because I'm not going to get into how I did that. But it was painstaking, let me tell you. So again, this thought experiment of this 5 by 10 window, you get 200 grams of desiccant in that spacer bar. And then you assume that airspace temperature is like 20 degrees. That's like the ambient temperature inside that airspace. And when you combine the data with the psychrometric chart, you get the desiccant moisture content on the vertical axis, and you get the IGU airspace dew point. And so when you use the frost point test or the spray test, you get that temperature on the surface of the glass down to like minus 45 or minus 70. And you can use this chart to say at minus 45, because that's that spray test. Let's just use that number. At minus 45, that says that if you get condensation forming right at that temperature, it means the desiccant has about 13 grams per 100 grams of desiccant in it, right? That science, I think, is pretty reliable. If you've tested the desiccant properly, you've measured the desiccant properly, and you use the psychrometric chart properly. So that translates to about 1/10 of a cup of water. So again, I don't know, just my feeling, and maybe some of you that are very experienced in this industry, like 1/10 of a cup of water, you turn that into water vapor and inject it into a sealed unit, you'd kind of think that it's probably okay. It's not going to fog at minus 10 degrees like in the winter, but if you challenge it to like minus 45 degrees, maybe it would start fogging, right? That just felt right to me. So I was like, okay, I did all these weird calculations and I sent this stuff off to a lab, pulled it out of some weird window that I found in the storage room. And it kind of all made sense. So this made me feel pretty good about what I was doing, because I thought this was, fairly technical stuff. So now I'm at the end. What does that all mean? What does that mean in terms of how long should your window last? Well, so I made this spreadsheet, and I didn't want to spend too much time on it because there's lots of numbers on there. I just wanted you to know that I built that spreadsheet painstakingly, late at night. It's not an AI generated thing. Like, look at all those numbers. It's a lot of numbers, right? And it took a long time to, like, if you try and find the permeance of PIB, you got to find many different sources. Anyway, but again, because it's not standardized, the numbers you get out of those calculations are widely varied. So in playing around with the numbers and kind of doing my own little parametric study, what I concluded was what I'm showing on this graph. If you just took two pieces of glass and sandwiched them together with a spacer bar and PIB, a little thin strip of PIB, no desiccant, and you stuck it in a window frame and left it in Vancouver, I would think, based on the numbers, that would be fog-free for about 5 years or less. And again, I don't know, that just felt right. I don't know if that feels right to some of you. Otto, you make windows all day long, right? Like if you... yeah. But still, I kind of thought, yeah, like a window could survive without desiccant. That made sense. But if you run through the numbers and you have a perfect seal with the PIB, and you put a little bit of desiccant in there, like a quarter of that 200 grams of desiccant, the numbers say you could maybe get 300 years out of your unit, which is, theoretically that's what it says, but that doesn't make sense in terms of reality. And if you had a perfect seal and you filled that thing up with desiccant and you ran through all my charts and calculations on my ridiculously complicated spreadsheet, you get like 1,000 years or more out of your sealed unit. So of course, that doesn't really jive with reality, I think. I mean, what lasts 1,000 years? I was just in Italy last year. There's a Colosseum there that's like 2,000 years old. It's pretty beat up, but there's no way an IGU is going to live for 1,000 years. Anyway, that's because the edge seal is subject to a lot of environmental degradation. There's wind action, there's pumping, there's atmospheric pressure changes, like Otto said. There's many different things that the IGU gets exposed to that obviously lessen the lifespan, that mean that 14 grams per 100 grams of desiccant of moisture that gets pushed into the airspace is going to happen a lot faster than 1,000 years. So I have one more data point. In the building that our office is in, we occupy 3 floors, and it was built in 1983, and you can go and look at the spacer bar and see how old the windows are. They're about 43 years old. And we frost point test those windows all the time, because anytime we get asked to go do frost point testing, we kind of test out our assembly to make sure it's all working, our machine and the dry ice is all working properly. So we've tested many of those windows in our office, and they're 43 years old, and we've never been able to make one of them fog up at minus 70 degrees. So somehow, after all those years, after all those decades, the windows are still good. So what I've concluded based on that other data point is that with good construction, with uncontaminated desiccant and a reasonably good PIB primary seal, you should get 50 years out of your window. So you're warranted for 10, but I think it's reasonable to accept that you should probably get 50 or more years. And so that's my presentation. That's all I have. Again, I'm challenged to try and find a better methodology to combine the science and convert it into some form of reality where you could do a frost point test, get to like minus 20 and say you've got 3 years left in your unit. We're not there yet, but maybe with some more research, we could get there. So that's it. Hopefully that was okay for first thing in the morning. A lot of graphs on there.
Excellent. Thank you. Question for Leonard? Anybody? Right there. That equation just pretty drastically between Vancouver and Winnipeg, though, I think, right?
Sure. Yeah, it's going to be different.
Yeah.
Sure.
Hi, Leonard.
Hi.
Fantastic presentation. That spreadsheet looks really painful.
Yeah.
My name's Scott. I'm with Quanex. Have you done any similar studies with warm edge spacer?
No, I mean, this was, again, I haven't done anything product specific per se. Well, you said the
warm edge spacer.
well, okay. This is not like a tube with desiccant in it, right? We're talking. We're talking like. Okay, I was just having a conversation with somebody about that. I mean, I've tried to run the numbers on that, but again, I'm not going to call out anybody's name here, but you call up the manufacturer and you say, what is this stuff made of, right? And it's got desiccant in it and it's got low permeability. So like, how does that work, right? The desiccant grabs the moisture, but it's trapped in this thing that doesn't allow moisture to get into it. So again, the science is there, but the data is not presented in a way that's usable And we did use that product on a building in Edmonton. And so I did try and go through that exercise, and I did, based on the data I got, I said, oh, the permeance and the desiccant is about equivalent to a spacer bar filled with those little round balls.
That's correct. I'll take this offline. I can get you that technical information on warm edge
Okay.
spacer.
Yeah, I'd like to get that. But again, you know, it took a lot of phone calls, and I had to go through a lot of different people to get that information. You can't just open up a textbook. Like if you want to find out the strength of 350W steel, no problem. And it's a reliable number within plus or minus 10%.
That was great. Thanks, Leonard. Real quick, if you do a dew point test and you do see condensation, does that condensation disappear, or is it?
Yeah, it'll once you remove the tester off of there, it'll disappear. Right. But again, if the unit is really in bad shape, you're going to get fogging occurring at ambient temperatures, and then you know that's when you got to replace the window.
I think 50 years sounds like a reasonable amount of time as well.
Over here.
Thanks, Leonard. I really applaud your desire to turn things into an understandable equation, right? Looking at the surface area and the different properties of the materials. I mean, I really wish it was that simple. And the thing I would like to say, though, is that sealed units, something they go through all the time. Well, for one, the manufacturing isn't a perfect science for any sealed unit or any system. There are sort of weak points in the manufacturing of it, and that's probably why you're going to get lifespans, much below 50 years, because I think most of us can attest that we've seen many failed sealed units that are not 50 years old. But the thing is that beyond the variables that are in there with the manufacturing processes, you've got also your regular pumping. You mentioned the word pumping, and that is that a sealed unit does, with pressure and temperature differential, pump all the time. So it puts strain on that seal. And in particular, PIB, that seal will get sort of squeezed out. You showed the squeeze out. And that's mostly due to the pumping action, not the initial squeeze out from manufacturing. So there's a lot of variables, but I really appreciate what you've done here and trying to put it in terms of some formula. And I think you should keep going on that. And there's different ways of measuring different things. And I'm sure it is very difficult to get that data to get those formulas to work, but definitely appreciate it. Thanks.
Thanks. Okay. I guess that's where that, back to that warm edge stuff, the mystery goop, sometimes I call it right? I think that might actually work better in terms of resisting that pumping action, because you don't have that PIB slamming up against that hard spacer bar. Sorry.
Yeah, there are, now warm edge is kind of a generic term for any system that is above or better than the old aluminum spacer bar. So even stainless steel is known as, that's the original warm edge spacer. Then there's different types of hybrid composite warm edge plus foam plus different types of extruded thermoplastic or reactive thermoplastic spacers. So there's a lot of different systems. That's a generic term, but each thing would be having different properties. So it'd be difficult you'd have to have a different formula for each one. But yeah, thanks.
Yeah.
Okay, over here.
Hi, Leonard. Over here.
Oh, yeah. Hey.
In regards to the pumping kind of conversation, the linkage between IGU size, exposure, wind exposure, glass thickness is generally driven by structural design, not durability. Do you see any linkage and any concern, or have you considered looking into architectural design where you get greater glass to frame ratio, and what a size limit could be to limit pumping that would extend the life of an IGU? Is there sort of a sweet spot or no-go zone where an IGU of a certain square footage is not recommended at a certain glass thickness because of increased pumping, which could shorten the service life?
Well, I mean, I've certainly thought about it, but you can read papers that try and model that, and like they try and model the PIB with springs. It's like super complicated, like math and physics behind it. So to try and layer that complexity onto this, I've certainly thought about it, but this was already causing my brain to hurt. Like that, by the way, in the office, we have a term for spreadsheets like that. We call them Lionel Richie spreadsheets, because you're working all night long to make that happen.
Ouch. Oh.
Hey, for the older folks in the audience, you'll remember Lionel Richie, right?
Hey, Leonard. In the pursuit to get ever better performing for thermal, we're seeing a lot of like proposals for thin triples, but they generally come up with very creative options for the spacers, even to the point of like cutting out the middle of an existing spacer. So I'm just trying to say, like, one thing I've tried to highlight to manufacturers is like, you may be chasing a metric without knowing the knock-on effect, where obviously this is a big impact. And I'm just trying to figure out, like, how is the information, or how better can the information be dispersed? Because it just, one metric seems to highlight that's what they're selling,
Right.
without understanding. Because, like, obviously this primary seal is not, you're gonna have some failures in a different way.
I think, that just makes me think of a more broader topic, like around windows and glazing. It's just the codes and standards are not as well developed as, whatever. I started out as a structural engineer. So when, you can go into a book and you can get, it's like steel, aluminum, wood, concrete, like it's all defined and there's no arguing. You use the number that's out of a book. But in the glazing industry, a lot of it's proprietary. Each manufacturer does their own thing, and they're going to try and show you the best parts of what they do and the other parts not so much, right? So it's hard. And the thin airspace is interesting because I always understood that 1/2 inch was sort of that optimized airspace for energy efficiency because of the convective currents that happen. So if you make the airspace thinner, that's going to affect your U values, which you can model actually reliably. Yes.
Leonard, great presentation. So I'm going to start with a comment and then a question. So comment, there is a project that NRC has started, and we're in discussions with them about durability of fenestration components. They're starting with IGUs. So this is all incredibly relevant to that conversation, which I hope we can connect after and we can talk a little bit more about that. Because I think there's opportunity to kind of start looking at some of things like size for those products, how pump is affected, and how some of the spacer bar strength. So anyway, so the question is a little bit of a crystal ball question for you. Given what you've seen from kind of this preliminary unpacking of the desiccants and what you see as far as lifespan, can you imagine a point where we can define the failure state for IGUs, which right now is essentially we get to the fogging of the inside, and there's probably even a certain level of how do we define how much fogging is a failure of that. But so the question is, if we could define a clear failure state, can you then define how long the IGU would last based off of testing through that curve, or is the curve too fast a failure to be able to deal with the numbers?
I think I think the answer is yes to that. And maybe I'm just an overly optimistic engineer, because that's really what engineering is. You take some scientific principle and you sort of grind it through its paces and find some empirical way to apply that theory in a way that's reliable. And again, things like, because structures are so linked to public safety, that research has been done. It's like you have these factors that are applied that are based on statistics to get to a certain reliability. So it's an agreed upon methodology to arrive at a number. And I think that's going to require buy-in from the manufacturers. But I think there is a state where you could do that because the science is valid, and you just need to relate all those parameters to sort of realistic things that you can measure and see in reality, and adjust them accordingly and grind them through your Lionel Richie spreadsheet, and you should be able to get a reliable number. And reliability is the thing, right? Structures are designed to have a certain, like a beta of 3 reliability, whatever that means. Statisticians know what that is, but you should be able to establish a methodology that will give you a quantifiable beta in terms of the reliability of the result. So I think that's possible. Just everybody has to agree upon how you get there.
Yeah, makes sense.
Okay, we're good. Leonard, thank you so much.
Thank you.
Appreciate it. Not sure that we on the West Coast, certainly the southwest coast corner of BC, really appreciate the lifetime of the IGU. I live in a house over on Vancouver Island. It's 47 years old. It's got about 50 sealed units in it, and almost all of them are original single seal hardbar units. Which is quite surprising, but the reality of living on the West Coast. If that house was in Winnipeg, those would have all been changed years ago. So yeah, it's an interesting topic, and like Adrian mentioned, we're working with NRC on durability, and that's a big part of that conversation is the life of the sealed unit and what that means to the durability and when product gets changed, et cetera. So, okay, so we're going to just take 5 minutes while I key up Cam's session. So if you need a quick coffee or something, but don't go too far, we're going to hear from Cam Drew on lean principles here in just a couple minutes.